Welcome back, AP Stat. This is part 2 of chapter 19. We're going to be talking about p-values, which we will see a ton for the rest of the year. When conducting a hypothesis test, after we collect data, we want to answer a question. Would our data seem strange if the null hypothesis were true, right? Just to review, in a hypothesis test, there are two hypotheses, the null hypothesis and the alternative hypothesis. Okay, for more on that, see part 1 of chapter 19. If the answer is no, our data would not seem strange if the null hypothesis were true, then we do not reject null hypothesis H sub 0. However, this does not mean we support a null hypothesis or say it must be true. We are not allowed to definitively say a null hypothesis is true, and we will talk about why that is the case later on in this lesson. But if the answer is yes, our data would seem quite strange if the null hypothesis were true, then we reject the null hypothesis. So depending on how we answer the question, would our data seem strange if the null hypothesis were true, that determines what we do with the null hypothesis. Do we reject it and support the alternative? Or do we not reject the null hypothesis? Okay, but we can never support or confirm a null hypothesis. That is not possible. To answer this question, we need a number. We need to find the probability that, assuming the null hypothesis is true, we could collect data at least as unusual or extreme as ours. Okay? And that probability is called a p-value. The p-value is the probability that, assuming the null hypothesis is true, we could collect data at least as unusual or extreme as ours. P has nothing to do with proportion, by the way. We see P related to proportions a lot, but P has nothing to do with a proportion, whether population or sample. It's called P because it gives the probability of an event. What is the event? Well, it's the event of obtaining a set of data as unusual as ours or more unusual relative to the null hypothesis. So a high p-value, in general, 10% or above is a high p-value. Really, it's a bit more nuanced. It depends on what you're studying, okay? But in general, say 10% or above, and a p-value of 0.1 or above, indicate that our data are reasonable if the null hypothesis were true. There's a decent chance we could get data as unusual as ours if the null hypothesis were true, if that is the case. We should not reject the null hypothesis if there's a high likelihood, and by high I mean 10% or higher, of getting data as extreme as ours. And again, 10% is a benchmark that generally works. Depending on what you're studying, that benchmark might be higher. If you're studying something in the hard sciences, your benchmark's going to be a lot lower. You are only going to be able to reject a null hypothesis with a very, very low p-value. But if you're studying, say, the social sciences, psychology, sociology, you can get away with very high p-values, well above 10%. It just depends on what you're studying. A low p-value, generally 5% or below, indicates that our data are not reasonable if the null hypothesis were true. Again, that 5% cutoff is just a general rule of thumb. Again, it depends on what you're studying. So that indicates data are not reasonable if the null hypothesis were true. Now, what about the gap between 5 and 10%? We will take things on a case-by-case basis, and I promise you, by the time we get to practice problems, by the time you get to the AP test for certain, there will not be any curveballs here. College Board is not going to throw curveballs at you concerning p-values. It'll be very obvious. All right, in the case that we get a low p-value, there's a low likelihood that we got data as unexpected as ours, given the null hypothesis is true. We should reject the null hypothesis. So the threshold for what's reasonable and what's not reasonable depends from study to study. More chaotic disciplines like sociology, economics, they're able to get away with very high p-values relative to that 10% benchmark. More precise disciplines like engineering, hard sciences require very low p-values. We compute p-values in this chapter using the properties of the distribution of sample proportions that we talked about in chapters 17 and 18. Since we're going to be doing hypothesis tests with proportions, we can use what we know about the distribution of a sample proportion that we started discussing in chapter 17. Here we go. Let's interpret some p-values. The smart wool analyst in our earlier example, that's from lesson 1, collects a representative sample, good on him, of visits since the new website has gone online, and finds that the p-value for the test of whether the proportion of visits resulting in sale has changed in some way, not necessarily for the better, notice, has changed, full stop, is 0.0015. And the p-value for the test of whether the mean sale amount has changed is a very different number, 0.3740. So what conclusions can she draw? Those are two different p-values. Think about what you would conclude, and then we'll see what our textbook has to say. All right, let's go on with this example here. If you want more time, feel free to pause the video, but we are going to move on. The p-value of 0.0015 is very low, you don't say. That means there is good evidence that the proportion of website visits resulting in sale has changed in some way. This is a low p-value. That indicates we should reject the null hypothesis of no significant difference and conclude that there is a significant difference in sales changing. All right? However, the p-value of 0.374 is quite high. Again, like I said, once we get to the examples, the practice problems, it's going to be pretty obvious what a high and low p-value is. They're not throwing curveballs at you. All right, this is a very low p-value. This is a very, very high p-value. Okay, the p-value of 0.374 is quite high. That indicates there is very little evidence that the mean sale amount has changed. Okay, so what do these numbers mean? That means if the null hypothesis in our first study, number of visits resulting in sale, if the null hypothesis of that study were true, we would have a very small chance of getting data like ours. So that hypothesis is very, very likely wrong. However, in our second study, whether the mean sale amount has changed, we get a high likelihood, all right, of getting data like ours if the null hypothesis were true. The null hypothesis being the mean sale amount has not changed, all right? Getting data like ours is very possible, all right? It's not over 50%, but it is a very possible outcome. So we should not jump the gun and say that the mean sale amount has changed in some way, shape, or form. We should conclude that we don't have enough evidence to say there's a significant change. Now we're going to talk about this gentleman on the right, Sir Ronald Fisher, and his advice about the null hypothesis. Note the terminology that we use concerning the null hypothesis. We reject the null hypothesis if our sample would be quite strange if the null hypothesis were true, and we do not reject the null hypothesis if our sample would not be strange if the null hypothesis were true, all right? So we have two options. Reject the null hypothesis if our data do not agree with it, and it's very clear because of a low p-value, or we do not reject because our data don't really seem that strange relative to what the null hypothesis predicts, and we have a high p-value. At no point are we ever allowed to accept or confirm or support a null hypothesis. If we do not reject the null hypothesis, it means that we don't have enough evidence to convict the data of supporting an alternative. Okay? That's that innocent until proven guilty. Just like in court, you can prove guilt, but proving innocence? I don't know. Guilt is something that you would prove. If you can't prove guilt, you assume innocence. Just like that, if we don't reject the null hypothesis, that means we don't have enough evidence to convict a set of data of supporting an alternative hypothesis. And here's a quote from Sir Ronald Fisher. Rejecting versus not rejecting the null hypothesis, the best way I have learned to describe why you can never support a null hypothesis is with this analogy involving swans. Suppose we were given this hypothesis. All swans are white. Okay? Suppose we collect a sample of 100 swans, and our null hypothesis is all swans are white. We would be able to reject the null hypothesis if we found a swan of a different color, like this black swan at the bottom right side of your screen, or a blue swan, or a purple swan, or a red swan, or a green swan, or a swan of a color that has not yet been identified. We would be able to reject the null hypothesis if we found a swan of a different color, because we'd be able to definitively say, no, not all swans are white. However, we would not have enough evidence to reject the null hypothesis if all 100 swans were white. There would be no evidence to contradict the null hypothesis if in fact all 100 swans are white. However, we don't know if all swans everywhere are white, so we cannot accept the null hypothesis as true. How do we know that the null hypothesis is true? Well, we would have to literally study every swan in the world, and to be entirely honest, every swan that ever existed. That is clearly impossible, okay? You cannot confirm that all swans are white. You can only deny that all swans are white if you find a swan of a different color. And that is how I can explain, and how I have explained, hopefully effectively, that you can never support a null hypothesis. You can only reject it if there is significant evidence. All right, now let's talk about the alternative hypothesis. So suppose researchers are trying to determine the effectiveness of a pill for the common cold. They're interested in the proportion of people who, quote, kick their cold in 8 days. That is the average time it takes for the average adult to be entirely rid of their cold symptoms. Okay, so you have an 8-day threshold here. Let's suppose 50% of adults with colds are rid of their symptoms within 8 days, while 50% have symptoms that linger on past that 8-day mark. It's kind of like an over-under, that 8-day mark for colds, right? If the doctors were curious as to whether the pill made some kind of difference, whether good or bad, their hypotheses would look like this. Null hypothesis, P equals 0.5, and alternative hypothesis, P equals 0.5. And P is the proportion of people who are through with their cold symptoms within 8 days. It's either equals or not equals. Null would be equals, alternative would be something different. This alternative hypothesis is known as a two-sided alternative, since we are equally interested in deviations on either side of our assumed proportion, the assumed proportion being 50%. Now, if doctors were curious as to whether the pill helped relieve people's symptoms quicker, their hypotheses would look like this. P equals 0.5 would be the null hypothesis, no significant difference from what we were expecting, versus P is greater than 0.5, which would mean that over 50% experienced early relief from their symptoms. This alternative hypothesis is known as a one-sided alternative, since we're only interested in a particular deviation, in this case, on the right-hand side, all right? A greater than 50% mark would indicate a deviation we are interested in, okay? Here is graphically a representation of a one and a two-sided alternative. Part A models a two-sided alternative in which both tails are of interest for a normal curve. Again, a normal curve is what we can use to model the sampling distribution of sample proportions, and since we're dealing with proportions in this chapter, we want to refer to our old friend, the normal model. B and C model one-sided alternatives in which only one tail of the normal curve is of interest. A small p-value indicates we are too far down the tail of the curve, in which case we reject the null hypothesis. So whatever p-value we get indicates how far down the tail, whether right, left, or both, of the normal model we are considering our study. So we use the normal model to determine whether or not we should reject or not reject the null hypothesis. Small p-value, we're too far down the tail of the curve, we reject the null hypothesis. High p-value, we're not very far down the curve, we do not reject the null hypothesis. Now let's do some practice problems. Number 1 is a fascinating and interesting problem. A research team wants to know if aspirin helps to thin blood. The null hypothesis says it doesn't, all right, so no effect on the blood. They test 12 patients, observe the proportion with thinner blood, and get a p-value of 0.32. They proclaim that aspirin doesn't work. What would you say? Well, here is what I would say. 0.32 is a high p-value, so at face value, we would want to not reject the null hypothesis. We would not want to reject the null hypothesis there, which means that we don't have enough evidence to reject that aspirin has no effect on the blood. But here's the problem with that. Though a high p-value would indicate we should not reject the null hypothesis being that aspirin doesn't thin the blood, we don't want to withhold a treatment that could work from someone who desperately needs a blood-thinning agent in a pinch. All right, for example, someone suffering a stroke. Just because we have a high p-value doesn't mean we should blanket proclaim that aspirin doesn't work. We do not have enough evidence to conclude that it definitively does work in all cases. However, in a pinch, we don't want to say, oh, aspirin doesn't work, might as well not use it. No, you do what you need to do in an emergency. So this is an instance in which we want to be careful about how we interpret a result. Let's look at our second example. An allergy drug has been tested and found to give relief to 75% of patients in a large clinical trial. Now the scientists want to see if the new improved version works even better. What would the null hypothesis be? Pause the video, give this one a go, unpause the video when you're done. Okay, let's look at the answer. The null hypothesis would be that the proportion is equal to 0.75. which would mean that the alternative hypothesis would be something different. And we want to see if the new and improved version works even better, so I'm going to go out on a limb. Here I am out on my limb, assuming that the alternative hypothesis is p is greater than 0.75, which will help us with number 3. The new drug is tested, and the p-value is really, really small. What would you conclude about the new drug? Well, that's a small p-value, which means we should reject the null hypothesis. We should reject the null hypothesis, assuming that the alternative hypothesis would be p is greater than 0.75. The proportion of students who experience relief, it should not have said students, I should have said individuals who experience relief, is significantly different than 0.75. Not just students, everybody.